All right. Structure of ionic compounds. So when we're looking at ionic compounds, they're going to have a positive charge, which is your cation, positively charged, and your anion, which is negatively charged. And they're going to be set up opposite charges. And those opposite charges attract, and they hold together things. Okay. Properties of these, they are non-volatile. What is volatility again? Do you remember volatility from our IMF discussion and a few other discussions that we've had over the years? All right. So volatility means if you have a closed container and you have this substance in here, all right, and that substance is now a liquid, so it's free to flow, you're going to have some of these go up as gaseous particles. All right? Everybody cool with that? But ionic solids don't have that property. Very little of it is going to go up into, oops, erased more of my jar went away. None of it's really going to go up into this. In fact, you're going to have to get this thing so stupid hot that, you're not really going to have it in a liquid state at room temperature, ever at room temperature, but rarely even in a lab setting. And you certainly probably wouldn't have it capped at that point either, because it would be generating a lot of pressure. Okay, as opposed to, let's say, like water here. If we had water, some of that water, most of it is in a liquid state, but some of it's going up into a gas state. Other things like gasoline or your fingernail polish. Let's use fingernail polish because you probably had some exposure to that. As long as you keep it capped, it's fine. But if you leave that cap off for a number of days, what happens? Huh? Fingernail polish. It's going to evaporate, right? Because it is volatile. Okay, it has low IMFs, which means that a lot of it's going to go up into this gaseous state. Okay, and that gaseous state, if your thing is capped, the gas will actually exert some pressure, which is called vapor pressure. Okay, we'll get into that when we get into IMFs again in Unit 3. But that's what that volatility means. Now, volatility doesn't mean flammability. They're not the same thing. Flammability means that we can catch it on fire. But a good portion of volatile substances are flammable substances. So one doesn't mean the other, but a lot of times they'll go hand in hand. Does that make sense? They have high melting points. They have to be broken in order to melt the solid, which separates into opposite charge particles. Again, very high temperatures. You're never going to have that at room temperature. All ionic substances are solids at room temperature, and they're collectively known as salts. So in chemistry, salt isn't just sodium chloride. It's any ionic compound. Ionic solids don't conduct electricity. So if you have a chunk of salt up here and you try to conduct electricity, it won't go through it. But because they're fixed in place. But if they're melted or if you dissolve them, then those ions are free to carry charge. And I kind of went through a little bit of that yesterday, I believe, in the lecture. Do you remember me? Many ionic compounds are soluble in solvents like water and insoluble in non-polar solvents like benzene. Why would they be soluble in water? What do you know about water? What do you know about polar and nonpolar.
One is sort of a same charge on both sides, and one is connected.
Okay. Yeah. So nonpolar means that molecule doesn't have a charge on either side. Okay. So no charge at all. When you have a polar substance, though, like water, so water is very polar. It looks like this. This end is going to carry your negative charge. This end is going to carry your positive charge. Okay. When it comes in contact with a ion, then the positive ion is going to get attracted to the negative end of the water, and the negative ion will get attracted to the positive end of the water. So if it's sodium chloride, you'll end up with your chlorines here, and then you'll have another water molecule off to the side here, and it keeps going, and it just surrounds that chlorine. And then on the opposite side, you're going to have your Na up here, and the waters are going to surround it with the oxygen end facing it. Good? Makes sense? And then one of two things is going to happen. You're either going to run out of sodium and chlorine ions to surround, or you're going to run out of water molecules to surround them. If the first happens, where you run out of sodium and chlorine, then it's called unsaturated, because you could add more in and be able to have it surrounded. If there's more sodium and chlorine than there is water, then it's called saturated. And there is a special type called supersaturated, but we really don't touch on that much in this class. Okay. Relative strengths, then, of these ionic bonds can be estimated by Coulomb's law. It states that the force is proportional to each of the charges, inversely proportional to the distance. So if you increase that charge, like we looked at some of 2,2, did you have a question, Grace? I'm sorry. Okay. Like if we looked at the 2,2 problem that Evelyn brought up a little bit ago, the higher the charge, the stronger the attraction is going to be. And that makes sense, right? Like if you had magnets and you had two magnets pulling instead of just one magnet pulling, it's going to pull it in tighter. Distance is also a factor. So things that have bigger, more electron shells are going to be a longer distance away from that nucleus pulling or attracting that opposite ion. Okay? All right. Potassium bromide has a higher lattice energy than potassium iodide. Why? Well, because the increasing distance between the charges is going to reduce the strength and the Coulombic attraction. I shouldn't have the answer on here. We should talk about it more, but anyway. Best laid plans. Are you looking at your chest correction? Oh, no, you're paying attention to your periodic table. Looking up silicone, thinking about your brother.
Mm-hmm. I'm looking at PR and I right now.
Particle diagram of rubidium iodide. What do you think, huh? Did I give myself another slide to do that in? Or nope, I did not. But I think I might want to do it on the next slide anyway, just to give myself more room. Did you need that up still? Did you get that all copied? Did I cut anybody off? All right, let's see where rubidium is on this periodic table here. Rubidium and iodine. So they are both relatively the same. So rubidium. And rubidium is going to have what charge? +1. It's going to lose an electron, so it can look like what? What does rubidium want to look like? Krypton. Yep. If it loses an electron, then it's going to be isoelectric whatever configuration, electron configuration with krypton. I don't know why I have such a hard time with that word. I just do. Okay, and then iodine is all the way over here. They're in the same group. But remember, this would have lost a shell, so it's going to be a little smaller than the iodine. The iodine, I want to try to draw a little bit bigger, and it's going to have what charge? -1, because it wants to look like xenon. Okay, and then we're going to have another rubidium here, and then we're going to have an iodine down here. Oh, not a plus. Get rid of that. There we go. And then a rubidium here. And then an iodine here. And I could keep going all day, but I won't. I'm bored already. All right, questions about 2, 3. Easy enough?
I know.
Ready to move on to some metals? Heavy metal rock. AC/DC. Van Halen. Lippy's dating herself.
My friends always made me listen to AC/DC.
I never really cared for hard rock much. I was more of a gentle, All right. So metals are going to be composed of cations that are embedded in delocalized sea of electrons. It's the sea of electrons that's able to flow and move through here that makes metals capable of conducting electricity, because that electricity can flow through those negative charges. Okay? You can't really tell from this picture which electrons came from which cation. You just have no idea. And we can flow those electrons through. That's what electricity is. It's just movement of electrons. And then how hard you push it, essentially. It all goes into physics, and I don't like that water, so I stay out of there. Chase is shaking his head as he's come off of 2 years of physics, I'm guessing.
Subject.
And then I just dip my toe in the physics pond. That's all I do in here. And get out of the water, because there's sharks in there. They'll bite you. And they're not baby sharks either, though. Number of valence electrons determines the amount of electrons that can be delocalized. When the charge of the cation and the number of electrons increases, then their attractions are greater. And that just makes sense, right? Coulomb's law. Back to Coulomb's law. Everything goes back to Coulomb's law. I told you they like Coulomb's law. All right. We can have mixtures of metals. What they have to do to create these mixtures is they have to heat up the metals, get them to a molten or liquid state, and then they mix them together, and then they cool them back down. So that's your brass, your bronze, stainless steel is made like this. So most of your metals are actually in alloy form when you use them. And there's reasons for that. They tend to be stronger. And in certain cases, they'll mix things in with them to prevent them from rusting or corroding. There are 2 different types of alloys that we talk about in here. Interstitial is the first, and that's where we fill in the little holes, which are called interstices, thus the name interstitial, with smaller atoms. So we fill those in. This is like your stainless steel. Okay, so when they make steel, and they they fill that in with carbon. And I think this was called like the Bessemer process or something like that. If I remember my history correctly. It was a big shift in the way that architecture was done once they came up with the process for making steel. Up until this point, they pretty much had wood structures. And those wood structures were only capable of going up about 5 stories high and still being stable. And so once they created steel, that allowed them to build, these behemoth skyscrapers that you see today. But, 100, 150 years ago, those didn't exist. Like, you went to a big city and 5 stories was about all you got. Now, there were things that were a little taller than that, like the spires in churches and that sort of thing, but they weren't really weight bearing. So you didn't have a lot of weight at that point where, trying to go across a whole floor level. So the other type that they talk about is substitutional alloys, and this is where the atom size is very, very close to the size of the metal atom that they're trying to displace. Okay? It's kind of like the difference between a kindergartner coming into my class and a substitute teacher trying to replace me in here. All right. Carbon steel is an alloy composed of a small amount of carbon atoms combined with iron. Consider the atomic radii of both carbon and iron and draw the model that describes the alloy that forms. So I think this is the drawn model. And what type of alloy would this be? Interstitial, right? The tiny carbons are going to fit into these interstices here, these holes. Easy enough? All right, we do. Label what type of substance we're dealing with here. Your options are the 2 alloys and a pure metal. Those are your 3 options. Andrew's like, I got this. Living. So this is a pure metal here. Okay. This is going to be a substitutional alloy. And this will be the interstitial. Easy enough?